Okay. Questions? Yes.
심포지 스테이트 정할 때
Yes.
이 스테이트는 보안 시간 이전에 풀 스테이트와 시간 동시로
Yes.
네. 다른 벡터 스페이스에 있는 두 벡터의 차이를 이해하세요.
있네요. So, okay. Conceptually, what we do is asymptotic states lives in interacting Hilbert space, right? And I can choose a basis of the Hilbert space. And in shredding a picture, those states evolve over time. Operators are static and states evolve over time. I'm taking, say, shredding a picture. Then I want to pick a basis for interacting Hilbert space. And therefore, this includes the entire possible dynamics, right? Because it evolves over time according to the full Hamiltonian. And then I want to somehow choose a basis such that it looks like a product free particle state in far past. Right? That's the choice. Now, mathematically, whether there's existence theorem, convergence, blah blah blah, I have no idea. Physically, I know it can be done, and it happens every day at the LHC. Right? So proton can say, oh, proton collide, like how far? Billion years, light years away? No, they literally happening right here, right? So from the perspective of a QCD dynamical scale, right? If I have a proton, okay, actually it's much further away from this because we are actually using 27 kilometer circumference ring, and they collide. And obviously, they are not 100% decoupled, right? There's electromagnetic interactions, there's gravity, there's this and that, and that. But at least practically, they almost decouple the state, and it's just one free proton, another free proton colliding to each other, right? And we just wanted to have a some more solid mathematical description of this phenomena. Now, but I think older people back in 1950, 60, presumably thought about this question deeper and more carefully. There's a notion of Mailer operators and this and that, and probably people thought about convergence and so on and so forth. So in that sense, your question is valid, right? One state lives in the one type of vector space, one Hilbert space. The other lives in the other. Like, what do you mean by comparing these two, right? Good. So that's a good homework assignment. and I think we will learn something at some point. So I mean, I'm not saying that you have to dig in and tell us, but think about it. And if you ended up getting somewhere, let us know. Okay, that's a good question. I don't have answer, like mathematical answers to the question. Yes.
I wonder something because 그 어심프트 스테이트라고 해도 그 결국에는 무한이동 과거의 스테이트를 아이디얼 힐버트 스페이스에서의 베이시스 벡터로 두고 거기서 스테이트 벡터로 정리를 한 거예요. 그 먼 미래에서도 아이디얼 힐버트 스페이스를 가정하고자 한 건데, 근데 그렇게 아이디얼 힐버트 스페이스를 가정을 한다고 해도 실질적으로 스캐터링 매트릭스를 계산을 한다고 했을 때 이니셜 스테이트 같은 거는 알아야 될 거잖아요. 네. 그러면은 그 이니셜 먼 과거든 먼 미래든 아이디얼한 경우라고 해도 그 이니셜 포지션이든 모멘텀이든 그 이니셜 조건 같은 걸 어떻게 정의를 해줄 수 있는?
Okay, let me see if I understood your question. So again, the question is related to the asymptotic state, and in the far future, we want to sort of label the state by some ideal picture. By probably, when you say ideal picture, you mean like looks like a product of free particles, and we have to therefore label them according to just the momentum of each free particle state. And so the question was, how do we assign consistent initial condition, also boundary condition at the t goes to minus infinity, also another labels as t goes to plus infinity. Did I understand you correctly? Okay. So let's imagine there is an actual mathematical limit where I had a state living in the interacting Hilbert space that actually looks like a tensor product of non-interacting free particles. Okay? And the formal question was, how do we see mathematically if this is ever possible? And I said, I don't know. But I know it happens and it works. Now, going back to your question, if such state exists, and if such thing can be formulated rigorously mathematically, although we really need that level, then since it really asymptote to product of n state, for instance, right? Then I can definitely, assign 4 momenta to each of those states, right? In this n particle state. Now, if the part of your question is whether this can always be done or not, the answer is no. This is not guaranteed to work all the time. Okay? Most of the cases that are relevant for particle colliders, it works. Okay? But sometimes there can be some situation where you imagine you have a 2 particle, but it turns out that they have a really non-decoupling interaction, even if you send them to infinity. In that case, they don't, the asymptotic state really are not sort of factorized into product of the free particles. And then there are subtle questions. Okay? And this is, so, this particular phenomena that I just described to you is actually one of the contemporary research. So when you try to think about collision of what's known as a magnetic monopole, and then electron, so electrical charge and a magnetically charged state, turns out that those 2 states does not actually factorize into product of the free particles. And there's a very interesting, subtle, and controversial phenomenon happens there, and people are still trying to understand that. But modulo this subtle subset, I think it works pretty well. Although there's another layer of subtlety. Let me just tell you the keyword. Another layer of subtlety is that suppose I have an electron interacting with the photon. It's a QED. Then, as you try to imagine like a state coming from like far past, and then do some QED interactions and then going out. In that case, there's another subtlety known as a soft collinear divergences. In other words, as electron propagate, because you want to see this is as if a free electrons, right? Because in the far past. As they do, they can actually emit the photons. But then, they can emit 1 photon, 2 photon, and then also at any possible angles. And then if you probably have to consider all possible such configurations, in some cases you can actually get divergent answers to those states. But luckily, people understood how to handle these types of subtlety in the sense of IR divergences, and then computing what's known as soft factors, and then doing Pariev-Coolidge formulas. There are some known established ones. So the story of asymptotic states are not free of confusions. So it's full of confusions. But I'm telling you that a lot of conceptual subtleties have been understood, but there are also remaining subtleties that we are still trying to understand. These are all valid and good questions. Any other question? Okay, so let's go. So today I want to finish the correspondence between Dyson-Wick expansion, right, as an operator expansion, and then a Wick diagram representation of that. After that, I will discuss Feynmann diagram, which is different from Wick diagram, and then we will hopefully for the first time start computing the amplitude, and then extract what is known as the Feynmann rules. Okay. So as a first, let's actually now establish the relation between Dyson-Wick expansion at one side of it, and then another side of it, which is Wick diagram. So the starting point of that was that we had an S operator we defined in the context of scattering amplitude, but now this is just an F operator, and then this looks like V for for x, interaction Hamiltonian. And we had a time ordering. So for that, we had a weak theorem, which says that if I had a chain of operators, right, basically it can be re-expressed in terms of normal ordering plus all possible contractions. Okay, is this actually working or no? Does this work? Yes. Yes, I also heard that. Right. So so last time, then what we discussed was that note number one. So I'm just going to go through features. First note, in this Dyson-Wick expansion, as a operator expansion, includes all possible normal ordered contractions. So obviously here I'm not skipping normal ordered contractions. Okay? Now when I say this all possible, there's a subtlety. There exists a subtlety, which I will discuss soon. And this is related to symmetry effect. Okay? So that's this side. But then that should correspond to, so this is arrow. Okay, let me actually use this arrow to actually make it explicit. So this arrow applies to this same one, not that one. Okay? Now, if you recall that Wick diagram, includes all possible permutations of vertices. Okay? So all possible contractions somehow has to match to all possible permutations. So in case you have already forgotten, let me remind you. So we looked at the second order imperturbation theory where I took the interacting Hamiltonian to be psi dagger psi phi. So this thing included the two different contractions, psi 1 phi 1. That included both. So one contraction we looked at was this. The other contraction we looked at was this. So diagrammatically, this was represented as 1, 2. So dagger comes out. So comes out. It was this diagram. So this is Dyson-Wick expansion side. I'm also drawing the Wick diagrams. So in this case, this will come out. So certainly, Dyson-Wick expansion include all possible contractions, obviously beyond what I have drawn, but I'm just focusing on one particular class. And then there's a correspondence. I mean, these two are related by permuting this interaction vertex length, right? X1 and X2. Now, keep going. Go to. Okay, so let me talk about that subtlety. However, there's a subtlety of a symmetry factor. Okay, so what is a symmetry factor? The definition of symmetry factor. So if I say that any diagram, so I'm going to use this D to denote a diagram, which can also be corresponding to particular contraction. So I'm going to be using D to denote the diagram, and sometimes I will also just denote as this, to just say that this corresponds to particular contraction appeared in the Dyson-Wick expansion. Okay? So then the symmetry factor is number of permutations of all these interaction vertices that leaves the invariant. Okay? So, for instance, let's talk about symmetry factor for this diagram. So you cannot find any permutation that leaves the diagram literally invariant, right? It leaves the fluid, charge fluid. So in this case, the symmetry factor is 1. We talked about it. What about this diagram? We also talked about this. 1, 2, that. So this, you have a symmetry factor being 2, right? And then we also talked about this. So in principle, here you can think about 4 factorial possible from permutations, but there are only 4 of them that leaves this invariant, like 1, 2, 3, 4, 2, 3, 4, 1, 3, 4, 1, 2, 4, 1, 2, 3. So there are 3 permutations that leave this invariant. Now, so that's the definition of symmetry factor. So what is that about? The important thing about that observation is the following. So then now, again, what is then statement in terms of this correspondence between the two? So the statement is that, so for instance, again, let's talk about that theory. It's easy to just look at the explicit examples. Okay. So let's look at this contraction. Okay, so that's literally bubble diagram, right? Now, the observation is the following. You may say, oh, this is represented as the following Week diagram. So that is how it is represented. You might say, oh, do I have another term appearing in Dyson-Wick expansion corresponding to this permuted version? The answer is, what I'm trying to say is that, again, I'm going back and forth between the two. On the diagram side, whenever you have a case where you have a diagram that doesn't change at all under any permutation, whenever this is the case, there's only a single term appearing in Dyson-Wick expansion. Because what are you going to do? So, this is fixed. You cannot think of any other permutation, any other contraction. So, therefore, the statement here is that all SD, let me just use this word, SD equivalent class of diagrams, okay? Take the diagram, do the any permutation that doesn't change anything. So this corresponds to a single term in Dyson-Wick expansion. Okay, so think about it, commit yourself. And this is basically. So this also represented by hand when they are literally the same. Okay, under the permutation. Okay, so keep this in mind. Let's go on. Moving on. So now we are going to define the following thing. So given a diagram D, okay, so let's consider a D1. Okay, we say D1 is equivalent to D2, so this is equivalent if D2 is obtained from U1 by permutations of vertices. So be careful. You might think that I'm writing the same thing over and over again. No, I'm writing every single thing slightly all different. Okay? So here I'm just defining a notion. I'm going to use this notation that I have two diagrams which are related by permutation of indices. And then we say that, in words we say that D1, D2 are the same pattern or topology. Topology in a super loose sense, physicist sense, okay? Basically, the best example, which was this, okay? Under the permutation of a 1 and 2, they are different, because if I fix this, permutation is related by that. They are different, but they are equivalent in this sense, okay? And then I'm gonna use the stronger notation, and then I will say D1 is literally equal to D2 if they are literally the same, okay? Example, spectral bubble diagram. And they are all embraced by this symmetry factor, okay? So whenever they're equal, there's only single term appearing in the Dyson-Wick expansion. Is that clear? Okay. Good. Now, I'm just gonna now sample everything. 4. So, S software will be an expansion of this one. Right? So far I've been talking about integrand. Okay? So here the statement is the following. If D1 and D2 are equivalent, meaning they have the same pattern, same topology, or related by the permutation of indices or vertices, then now this is equal. So any two diagrams which have equivalent topology or they're related by permutations, right? But obviously, when you integrate over entire vertices, it includes all possible permutations of integration. Just imagine in one dimension, you have x1, x2 living on a one dimension. But if you integrate, you have to integrate x over entire line, also x to entire line. Sometimes you will have this, sometimes you will have that. So integrate over entire vertices, perform entire possible permutations. Okay? So if two diagrams are related by this permutation, therefore they have the same pattern, once you perform this integration, you will get the same numerical answer. Sorry, not numerical answer, this operator answer. Okay? Yes.
I just wanted to check for one of the diagrams that we drew, the one with SD, like the symmetry factor equal to 1, with the charge flow going separately. Are they equivalent or not?
You're talking about the diagram I just raised?
Yeah.
They are not equivalent under the permutation.
They are not.
Sorry. They are equivalent only in this sense.
Yes.
But not equal.
Yes.
Okay. Yes. Okay. Yes. So that's the subtle difference I want to make sure. Okay. Good. And finally, note 5, which are not super significant statements, but nevertheless, let me say it just to make sure. And then I will write down important formula. So weak diagrams are defined up to topology. Okay, if this scares you, don't worry about it. What I mean is just this. Suppose let's consider one diagram. Okay, so this should be literally equal as a diagram. So I just literally flip these two. Okay, I didn't do anything. No, not even permutation, nothing. I'm just literally take the same diagram and then I just deform it a little bit. Okay, or I can do whatever. I can even flip over everything down. So they literally represent the same diagram. right? This is not about the permutation, this is not about the symmetry factor. I'm just saying that the Wick diagram is already defined up to all these topologies, right? You ask different people will draw different way, but they are drawing literally the same object. Okay? I feel like, let me just draw one more thing. So here's one Wick diagram, but some people might draw that way. It's still exactly the same. Okay, now I'm ready. So now let's recall. Dyson-Wick expansion included all possible contractions, normal order contractions. And then the corresponding feature on the Wick diagram side, it included all possible permutations of vertices. Whenever you have a diagram which is related by the permutations, they are the same topology pattern. Some of them, that diagram doesn't even change. How many number of them? Symmetry factor number of them, right? And all those equivalent class just correspond to single term in the Dyson-Wick expansion. Okay? So now going back here, so there will be a lot of contractions living here, right? So this will give you a lot of contractions that fixed order in perturbation theory. This will give you a whole bunch of things. So for instance, okay, so there can be so nth order perturbation theory, and then there can be, first kind of pattern, and then there are equivalent class, meaning this include all possible things up to permutations of vertices, right? And then there can be another, so basically we are reorganizing this. Second possible pattern, you might have a many different kind of thing, I don't know, right? So now we are just reorganizing this expansion. Dyson-Wick expansion in terms of diagrammatic expansion. So let me actually now write the following thing. So here's a claim. So nth order. So here's my time order product, and so then this has its own story in terms of Dyson-Wick expansion. But I'm gonna write now exactly this correspondence. So at nth order, I want to sum over all possible patterns. Okay, and then I want to say that corresponds to Pn contraction. So even though I'm writing as a normal ordering, I mean this is a diagram. Okay? How many number of them? How many distinct number of such diagrams? The question is. So for fixed pattern, for fixed topology, how many distinct diagrams do I have to talk about? So for instance, in this case, I will have two distinct diagrams, right? Because they are distinct. For vacuum bubble, I will have only one. Even though naive permutation gives me, I have to have two, right? But I only have one. Another example, what about that? So this also is included in the second order perturbation theory, right? Again, under the permutation, you get the exact same diagram, which means that on the Wick contraction side, there will be only single term, single contraction appearing there. So even the naive, on the diagram side, naive permutation suggests you might have two, but they are related by symmetry factor, there's only single term. Okay? So you might say, naively, there might be n permutations of things, so that's what you can try first, right? But the claim is that not all of them will give you a distinct diagram. So you have to divide it by symmetry factor. So that is the number of distinct actual diagrams. For instance, 2 versus 1 in this case. Okay? Good. So once this is understood, now we can write down a full formula which gives you precise mapping between the operator extension and the diagram. So here is the interaction picture and evolution. at the price of being redundant, let me write again. That's so therefore this is equal to n, sum over n. And then for each fixed order, I have to sum over topology, diagram pattern. 1 over n factorial is cancelled by this 1 over n factorial. Oh, everything is good, but let me just define one object. So let me define one object, and then I will finish writing the answer. It might be better, instead of writing twice. Let me define one object. So O, the nth order, a given topology. I'm just going to define that as minus 1i to the n, and then all this integral, we're not even like an e for x, and then a particular dn pn contraction. Okay, so that's my definition. Then, so basically here, I'm just eating up everything except these two factors. And that is cancelled by 1 over n factorial. Symmetry factor is left out. So this will be basically divided by symmetry factor. So that's what we wanted to establish first. Okay? So full S operator is represented by sum over every order in perturbation theory, and with the fixed n, there will be a number of different patterns, different diagrams, topologies, and then I need to compute one of them divided by the symmetry factor, not entire n factorial and so on, because once you perform the integral, every diagram that falls into the same topology will spit out the same answer. Right? There's integration also basically make all different permutation equivalent. Okay? So that's the correspondence. Good. Now we will improve. So this is not the final destination. This is a good intermediate step, and we will improve further. Any questions so far before I move on? Yes.
Are the diagrams equivalent?
So, I mean, they are equivalent in this sense. They have the same pattern, meaning they're related by the permutations.
The S matrix only includes modular of that diagram.
Exactly. So, for instance, I need to include one representative of that, right? So, from each of the equivalent class, I'm just gonna pick one representative, right? Because this will basically add up. Basically, this is counting number, how many numerical factors I have to multiply for a representative of given topology. Okay? So for instance, this topology has two distinct diagrams, but I just need to compute once n times 2. This equivalent class have literally one guy, so I need to compute 1 times 1. Okay, if you had another topology that has like Q actual distinct diagrams, but you still need to compute one of them, and then times Q, and so on. So that's what this is basically having. Yes?
Is there some sort of mapping in terms of like graph theory or some sort of representation of the graphs that we can use? Because this is a very computational formula. It seems that the symmetry, we just like look at the graph, or is there some sort of, I don't know, matrix representation for the graphs?
Good. So here, this is somewhat, in a sense, formal, in that we wanted to understand, given this expansion, what is the actual sort of a mapping or correspondence between the two. But in practice, also to have actual like computations and any sense of a diagrammatic method to use it, we are not going to spend much time actually at the level of S operator. Instead, we're going to spend most of our time talking about final state and then S operator initial state, transition amplitude, which is number. So after this, we will develop a diagrammatic method for this, and then the rest of the QFT, staying in the perturbative theory, people will only use basically this diagrammatic method known as the Feynman diagrams. So this is a proof of principle conceptually, that there is such thing exists.
Where did that n factorial go in the final?
They cancel against the order of n factorial. Good? Okay, so now let's improve this, because this is still quite redundant in the following sense. Let me improve that. So there's this notion of there's this notion of disconnected and connected diagram. If you like, this is sum of all possible diagrams, right? By all possible, I mean all possible, possible real-looking diagrams from each of these classes. And this can be a redundant. We want to find a basis of diagrams, and we want to represent the entire diagram in terms of this basis of diagrams. So here is the example. Suppose I want to look at, again, okay, slightly different, because you probably get bored of the same diagram. Yeah? So here's one diagram. Another version could be, I can look at this process, for instance. This shares many similarities because they have a four vertices, and a two internal propagator, two internal propagator, although this one has two more internal propagator. There are common features and differences. But for the discussion that I want to deliver now, what matters most is that this is connected in a sense that, it's connected. And this is disconnected in a sense that, this consists of two completely separate case. So here's one case, and here's another case. Okay? So for instance, if you knew how to compute this one, also if you knew how to compute this one, you don't have to compute this separately. Just recycle your original knowledge as product of these two, right? To generate this new computation. So in that sense, it's redundant to keeping some description that this is treated separately from individual connected pieces. So therefore, certainly a space or set of disconnected diagrams are very redundant, and a set of connected diagrams for much smaller set of diagrams, it turns out that in fact a set of connected diagrams is sufficient to generate entire diagrams. Okay? So for instance, therefore, to make the discussion more precise, let me define a set of connected diagrams. So this is C. You note that I'm talking about only connected diagrams. And then suppose there's a concept that I know the entire set of connected diagrams. So for instance, this R goes from 1 to innumerable set, like infinite, for a given quantum field theory. Okay? Then the question is, can I rewrite this one, right? This one include all disconnected diagrams. Can I rewrite this in terms of only a connected diagrams? So that's the concept. So the claim, and then I will illustrate why that's reasonable. Claim is O of anything like this can be written as O of some number, and then I just do entire product. So this is a claim. Let's see why this makes sense. So let's take again an example. Suppose I had a process. Let me see. So I had a 5 of this, 3 of this, again 5 of that coming out, 3 of that come out. Suppose I want to look at this process at collider. So in this theory, particular example of theory that we've been taking to illustrate the point, for instance, this can be represented as the following horrendous diagram. Oh, do I know the answer? Do I know the answer? Okay, let me see. Boom. 1, 2, easy. 3, am I successful? Oh, sure, right. Okay, so that matches all the external links, right? And, well, I can throw in some random vacuum bubbles too. Yeah? So this will contribute to this process. More precisely, this diagram, Week diagram, will contribute to a term that looks like this in the Week expansion. Yeah? But then you see that this looks like basically, I'm not being careful about the arrows right here. 3 times to the 1 times square. Yeah, I'll come back to you. Can I finish this and I'll come back to you?
NR.
I'm sorry?
NR.
NR.
At the top, right? Next to the power.
NR. You know what this is?
What is it?
Yes, I'm about to explain. Yes. The 0, you name it, whatever you want. To the 0, any diagram that doesn't show up here, you'll just get a 0th power. So the point here is that any diagram can always be represented as a product of only connected diagrams with the proper power. So in this case, NR for this diagram it is 3. For this diagram it is 1. This diagram it is 2, and the rest is 0. And then I just take the product of the entire those things because this is basically operator representation. Is that clear? Okay. So that's first claim. What about this one? Symmetry factor, combinatorics, edit. What about that? Turns out that's also not too bad. So let me just answer that, and then we will have a slightly more elegant version of that. So let's talk about a symmetry factor of a possibly disconnected diagram. Let's keep this in mind. For a given diagram, there will be a symmetry factor on its own. Yeah? So this will have a symmetry factor of a basis connected to this. But if this consists of an R copies of a particular R connected diagram, there's a symmetry factor for each of them, right? So this will be this to the raised to the NR. But also, if I had an identical NR number of one class of diagrams, I can permute them without changing any diagram at all. Right? Remember, symmetry factor is any kind of combinatorial permutations that does not change the diagram. So I can just permute this, but I have to now have a product of all this. Okay? So after that, then I can rewrite this as follows. This is equal to N, and then, okay. So I'm gonna fix it, but I'm gonna first write this piece first. O drc divided by this one. Oh, to the n. So to the n. to the NR. Well, I can just put inside, so let me just rewrite. ODRC to the NR divided by, I'm just writing now, symmetry factor, NR, and then I had a 1 over NR factorial, yeah? And then I had a product, so that's integrand, okay? So I have done the integrand, so this single term, sum on, if you like. What about that? This is basically sum over entire ordering perturbation theory, all possible topologies, right? So they will be taken care if I sum over every possible powers of NR. Okay? So I just choose how many number of them I just insert. Okay? So this will be sum over N1, 0 to infinity, you keep going. 0 to infinity until infinity, right? So that sum will take care of sum of entire possible orders and topologies. Okay, so we can clean up better. So suppose I call this is a gigantic function of NR, because I'm only summing over NR, so let me just call that a gigantic function of NR. So this looks like, this particular structure looks like sum over N1, sum over N2, keep going. And the product of R, and then this is a product, so I can actually, let me just write, so f of N1, f of N2, keep going, right? That's the structure of that expression. So I can rewrite this as sum over N1, f of N1, sum over N2, f of N2, and then entire product. So the claim is that this can be rewritten as a product of R 1 to infinity, so product over entire basis of diagrams in connected sense. And then I have sum over 0 to infinity, and then object. Factorial, let me just embrace everything inside of it. 2 NR. So that's 1 to infinity, and that's formal expression for exponential of O ER, S ER. So you have a product of all these things. And that thing is same as sum of 4R okay, so that's the final expression we wanted to get to completely establish this. So let's actually look at it and digest. So what we have achieved is the following. So we started out with the S operator, which is this basically interaction picture, time evolution operator. Yes?
Can we do that because the graphs are disconnected?
Can we do that? Is that which piece? Which part?
The final one. The final
this?
Yes. Because do the scattering operators and all commute?
Yes, this represents a particular weak diagram. Well, that's exponential. So the product is that whatever this represents, right? This represents the horrendous diagram. There's a one boom diagram, and then there's a product of another diagram, another diagram, another diagram. So this is, you have to understand that there's a formal meaning inside this equality, and I'm just saying that this is a product of this line is a product of these diagrams, and this is saying that no, if you take exponential of a sum of all possible connected diagrams, modulo symmetry factor, and then if you expand, this will generate the product of connected diagrams. because this way the x squared, x cubed, x to the fourth has an infinite series. So each of those terms appear in the Taylor expansion in formal sense. We represent the product of diagrams. So again, going back, starting from this, and then Wick's theorem, we know how to expand this in terms of normal ordered contractions. Now this was the first establishment of this fact. So you have order by order you expand, and then at a given order there is different topologies of diagrams. Okay? And in a minute, different topology will represent the different physical processes. Vacuum bubble versus Hurto scattering, for instance. Okay? Then there is a representative of diagram. Oh, I erased it. And then you have to divide it by symmetric factors. That was the precise establishment, in a sense, between this and that. Now, and then we say this is redundant. So any diagram can be represented as a product of connected diagrams. But once all the dots are settled, basically once you exponentiate, you only need to keep only connected diagrams. So connected diagram is a basis for the entire diagram, connected, disconnected, whatever. Okay? So that's the establishment. Any question? Now I'm about to move on to the next.
And if you consider every sum over Rchen, 그러니까 R에 대해 전부 다 합한다고 한다면
So say it again?
저기 R에 대해서 전부 다 썸을 하는 거잖아요.
Yes.
그래서 R이 그걸 하이트 다이어그램 어쨌든 순서를 매긴 거긴 한데 거기에도 퍼터비티브 오더가 있을 거잖아요. 근데 만약에 저희가 세컨드 오더까지 현실적으로 고려를 한다고 치면 그냥 그 오더까지만 구해주고 끝내면 되는 건지 아니면 저 식 자체는 모든 R에 대해서 수학적으로 성립하는 그냥 클레임을 끊는 거죠.
Good. So let me address that question by just actually taking a specific example. That's important because you have to play out. You have to play with these expressions. You might say, beautiful. Okay, I just learned it. Done. It will not become yours. So again, let's take this example to really appreciate what that actually means. S operator is the exponential of, okay, plus. Beautiful thing is you have to keep track of the symmetry factor, right? Correct? But let me be sloppy about that. And then that's the first order, right? First order. And then what about the second order? Second order we had this. Yeah? However, remember the definition of this O included the minus I to the power integrals. And then contraction, particular contraction of that graph. Okay? So in the sense, if you had any diagram which are equivalent in the sense that they're related by permutation, because of this, they correspond to a single object appearing. Okay? So I'm not gonna draw the other one. And then you can think about whether there's any other diagram at the second order, and then you keep going, right? So, there's another diagram. For instance, you can have this. So anyway, so it will be the infinite sum. Now, going back to the question, suppose I'm interested in having this at the second order imperturbation here. Right? Again, I'm not putting the symmetry factor right, but I will. What are the possibilities? You expand. So you expand 1 plus linear and then square and then cubic and you keep going. But obviously you understand that you don't have to go to the cubic of this expansion because that's necessarily higher than g to the cube. So then square order, this will be one contribution from the square of this, for instance. And then every single one bit of this. If you go to the higher order, for instance, cubic order, you have a product of all this. Fourth order, you will have a product of this too, but also there's a genuine fourth order diagram will contribute to it. So you see, it give you up automatically because that's how we build up this. Correctly, the whole contribution, once you specify your truncation, I want to get every diagram validated up to g to the fourth. You expand, look at all diagram that is up to first whatever g to the fourth we are interested in. And that will contain not only fully connected diagrams, but also disconnected diagrams. Okay, does that, if that doesn't address your question, try again. Good? Okay. Okay, so that's that. Now we will switch our gears to the Feynman diagrams and the Feynman rules. If you have any questions, please let me know. Most likely, you're not going to use what we discussed today in daily lives. Well, first of all, most likely, not most of you actually use this type of script anyway. But suppose you are one of those people who will use or have to use this type of QFT. But nevertheless, you're not going to use the particular discussion or argument that we had today on a daily basis. But at least you want to understand this is the way QFT has been constructed. You want to know how solid, is there any room, and how to think about, especially combinatorics. Physicists like socks at combinatorics, right? 2 factorial is the best you can do. But at least you want to think about correctly that this works, and then you can free yourself. Okay, so with that, I will again switch my gears to Feynman diagrams. And as I already mentioned at least once before, what we are ultimately interested in is this transition amplitude. Okay? Starting from the initial state, which is now characterized in terms of a product of free particles, and going to the final state, which again consists of free particles. So maybe this is labeled by a P1 to Pn, so there's an n particle in state, and then K1 to Kn, so there might be an n particle in our state. So again, the picture was we want to send in P1, P2, Pn, so there's an n free particles, and then K1, K2, and Kn, and outgoing state, and then there's a localized region of space-time that something happens, characterized by this interaction picture evolution operator, right? And then this, for a given choice of this, for a given choice of that, for a given choice of this, when I say for a given choice of an S, you are picking a specific theory, right? Then this will tell you the answer. What is the probability of this in state going into the out state for this particular collision process? And we can compute it order by order, right? So now you see that instead of an S operator, which was the story we talked about so far, we are interested in this transition amplitude. Okay, or scattering amplitude. And we want to develop a diagrammatic method to compute the amplitude rather than an operator, but that is this Feynman diagram. And then we will eventually extract and then make our life easy, a set of rules that we can just memorize those rules to compute easily, instead of going through horrendous algebra exercise, which I will have to demonstrate, unfortunately, today. Okay? So, but I will ease my life a little bit, in a sense. I'm not going to do an instant job from the beginning to the end, but at some point you will see appearance of HW, which means homework problem, and then I'll just accelerate my process. Okay, so but before that, let's make sure that the scattering amplitude is labeled. Okay, I have a trouble. Labeled 2L, 1L. Who's native speaker? 2, very good. Labeled by N in state, M out state momentum. Okay? So there's N in and out momentum. Now, this needs to be contrasted with the Wick diagram where we've been focusing on x1 and x2. We were not interested in like the momentum of this guy. Okay, we kept, okay, where is the first vertex, second vertex, permutation, all of that. So first of all, key difference is that when we start talking about amplitude, we have to talk about object defined on the momentum space rather than the Poisson space. Okay? So the first note. I don't know if it is actually. Maybe I shouldn't say is. Slightly different, but let me give you hope, even though it will fail to be the case eventually. Easy combinatorics of it. Combinatorics. Although it's more precisely, it's a different combinatorics, but it won't be as horrible as we have got. Okay, so let's see. So to illustrate the second point, hopefully this makes sense, right? Position space diagram versus momentum space diagram. So let's again take our lovely theory. We'll never get out of this theory this semester. Okay, so we will again take this theory. And then suppose psi had this suppose alpha annihilate the particle, and then the particle state, let me just label as n following Feynmann, and then beta dagger, which creates antiparticle, which let me use n bar. So this is based on history, because all days, today we don't talk about as an elementary particle collision in terms of the neutron. But back in the day, when Feynmann was actually thinking about it, neutron was one of the fundamental particles. Okay, so they wanted to talk about the scattering of neutrons. Okay, so that's why ends, but doesn't matter. Name is not important. Okay. So taking this, and then this will do whatever it does. Okay, the real scalar, and it creates another same particle. Now, to illustrate the second point, let's consider n goes to n process. Okay. So, what will be the diagram in momentum space that actually does this? So, it will be something like this. N have to come in. Remember, whenever the charge flow is parallel to the momentum flow, that's the particle. Okay? And then I have to have this. We cannot connect these two because then there's a charge violation. So it will be this. I'm taking this as my time direction. Okay? So n goes in. So now I have to label my momentum, which I will do. And then n comes out. So let me actually label the momentum. So let me call P1, P2, K1, K2. Okay? And there's another diagram which looks like this. I'm doing this to illustrate the point that these diagrams are defined of the topology that actually exactly look the same as this, right? So again, there's a P1. So now, actually, let me just put P2, K1, P1, K2. So what I have done between the first and then the second diagram here is I swap P1 with P2, right? That's what I did. So you may say this is actually the same as drawing this. Let me see if I can do this. Can I do this? So my P1 linked to the K2, P2 linked to the K1. Okay, so that's the same diagram. Okay. Now, there's one important thing that we have to keep track. So, in principle, in this case, there's an intermediate propagator. So, if I choose the direction of momentum to be this, there's a Q here. And then there's also a Q here. So, let's figure out what those Q momentum transfer is. Okay? So, this Q, by momentum conservation at each vertex, there are two lines coming out, one coming in. So, coming in should be same as two coming out. The Q should be equal to P1 minus K1 in this case. Here two. Two comes out, one comes in. So they have to add up to the same. So Q should be P2 minus K1. Okay? Now, first of all, they must represent a different contribution to the same scattering. So definitely this is n collision to the n collision to the n. It should correspond to the same amplitude, but they are physically distinct, right? So one kicks the intermediate guy with this momentum transfer, second guy kicks the intermediate particle with a different momentum. So it corresponds to the different contribution to the same amplitude. Okay? So let's understand the physics of it. So first there's n coming with the momentum P, and then here it's split into a outgoing n with intermediate real scalar phi. It kicks the intermediate guy with this momentum, and then at some point, another space-time point, it meets with another initial particle with the P2 and turning into the final, right? You can do the exact same interpretation of that, but I'm doing it such that you can understand that these correspond to two physically distinct contributions to the same physical process. Same, and goes to end process. Okay, I'm taking a pause now if you have a question, because I'm about to add two more stuff here, which can confuse you. So I want to take a pause now. If you have any questions, let me know. So I'm still taking a pause. I'm just enjoying my drawing. So let me call this my vertex point 1 and 2. Let me use. Okay, it doesn't matter which way you label 1 and 2. Okay, so yet another layer with a fixed vertex point. I'm telling you that there are two different distinct cases. But then you can say, oh, on top of this, there can be two more diagrams with vertex 1 and 2 are exchanged. Right? So I can have the exact same copy for label 2 and 1 like that. Exactly same copy, but like 1 and 2 like that. Right? Now, the claim is that this, so let me therefore, so let me call this first diagram to be A, the second diagram to be B. So 1, 2 exchange the version of A, so let me call that to be C. And then there's a 1, 2 exchange version of B, let me call that to be D. Okay? The claim is that this will make exactly the same contribution as this will make exactly the same contribution as that. Let's understand. First of all, whether I call it 1, 2, 2, 1, momentum configuration-wise, they are identical. And if we know that the S matrix for scattering amplitude is the function of external momentum only, and this one has the exact same topology, same momentum data, if you compute this thing, which we will do, you get the same function. Right? So permutation of vertices does not give you a different function, different scattering amplitude. They give you the exact same function of external momentum. Okay? Here too. So therefore, it's a slightly different way of slicing now the diagram space. So now, if you recall, now there's S, and then whatever, n factorial, you have all kinds of stuff. So there's this n factorial. However, in this way of computing now, which we will demonstrate a scattering amplitude for any given Feynmann diagram. So let me just now give a Feynmann diagram, right? For any given fixed vertex, 1 to n, and then with the same fixed momentum assignment, then you can just go another permutations, and this will completely n factorial number of them, okay? And they just give exact same contribution, as I said. So basically, we don't have to worry about this n factorial factors. To summarize, now, just make sure, in case you think, oh, where this is going, I'm now arguing just based on heuristics first, right? I'm first setting up the stage to argue or discuss what we would likely expect, okay? And then I will actually do a specific calculation to confirm the expectation. So in case you're worried that you don't actually get like precise logics line by line, don't worry too much about it. We will eventually carry out precise calculation, confirming the expectation I'm setting up now. So therefore, to summarize, what I was trying to do here is that just based on the understanding that we should expect a function of external momentum, which is the scattering amplitude, and then if you want to have a diagrammatic representation of those processes, what we have to worry about is not the permutation of vertices. Rather, we have to worry about different momentum assignment. In a sense that initial, final, in particular in this example, the intermediate momentum transfer. Different momentum configuration correspond to distinct, different contribution to the final scattering amplitude. But for a fixed momentum assignment, any permutation of vertices will give you identical answer, and that identical answer anyway will cancel this out. Is that clear? So that is where we are going. So next time, what I'm gonna do is that first I will compute this, okay? Just by honest gut calculation. Starting from this, there's a time order expansion, there is normal ordering. We're gonna actually compute it. We will see actually that it will pops out automatically these 4 terms. We will see that the term that corresponds to the C and D make the exact contribution as A, and then D exactly make the exact contribution as B by actually doing computation. So we will get eventually a function of external momenta as a final answer, as it needs to be. And after that, we will now extract the rules. Okay? What will be now mnemonics you can build to easily compute those answers. That will define our rules. Okay, so that's the logic we are heading. Yes, you have a question.
So then in the next class, do we use Week Dyson-Wick or?
Yes, yes, exactly. Because that's all we have at the moment, right? So we are going to use yeah, exactly. We are going to use a Dyson-Wick expansion, but in the context of transition amplitude rather than operator. So we will have P1, P2, K1, K2, like that, right? And then we compute it and get the answer, which is just a function of a momentum. Understanding these expectations. Yes. And then after that, we will forget about the Dyson-Wick expansion once we have that. Okay. Any more questions today? Yes.
짧은 질문인데 저거 바로 안 떠오르는데 기본적으로 몇 개는 외우는지 좀.
Which one?
다이어그램.
Oh, you worry that this doesn't come to you immediately.
지금 직관적으로 그런 것들이 있다는지 안 떠오르는데.
Yes.
그냥 저런 게 따라서 어느 정도 기억을 해두고 계산하다 보면 알겠다.
Obviously, I can pop it up because I learned it before. I prepared the lecture. But if this is literally your first time learning this, right? I don't think Feynman came up with it like, yeah, of course, right? He struggled and computed it, and is there any simple way to do it? So don't worry too much about it. Even if this did not happen immediately. You're not supposed to make this. Okay, another question. Okay, if not, we will, today is Monday. On Wednesday, and probably TA sent out the link to the doodle. Please respond to it as soon as possible because we need to come up with a makeup plan. Okay, we are running out of time, basically, so we need to make it. Thanks.